Alright, Mr. Palmer, I'm going to do a quick video on an intro to binary. If you're doing A-level and GCSE computing, you can watch this video. However, I will tell you if you're doing GCSE where you need to stop. Okay, so basically the big question for this video is how a positive and negative binary number stored in a base 2 number system. So our number system that we use to count in daily life, okay, we've got 10 numbers. Okay, we call it the denary number system. Some people call it decimal. 10 numbers, so we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so basically if I've got 7 plus 1, I'm going to get 8. Alright, and now if I'm doing 9 plus 1, I'm going to actually have to now move into the next column because the value that I want to store is too large to hold within a single digit. Okay, so I've got my units column, and then I have a tens column, a hundreds column, thousands column, etc, etc. So basically the denary or decimal number format is used a base 10 number system. Okay, so the column placeholders are calculated using tens. So the right hand column is 10 to the power of 0, the next column is 10 to the power of 1, the next column is 10 to the 2s, 10 to the 3s, 10 to the 4s, etc. So when I'm storing a number, okay, putting one digit in each column, alright, and then that digit has a value based upon the column placeholder. Alright, so 11 is going to be 110 and 11, 108 is 100, no zeros and 8 ones, etc. And we add up each of those individual values to get the total value for that number. Binary is a base 2 number system. So like in denary we had 10 numbers 0 to 9, in binary we only got 2 numbers 0 and 1. That's all the computer understands. We use binary because it corresponds to the two states that a transistor can be in, either on or off. Alright, so a binary number format will still allow us to store all the possible numbers that we want to store, but the column placeholders are slightly different. This time, instead of going up in twos, instead of going up in tens, we're going up in twos. Alright, so the decimal or denary equivalent of each of those columns is going to be this. 2 to 0 means I can store 0 or 1 in that column. The next column is 2 to the 1, so it's going to store 2s. The next column is 2 to the power of 2, so it can store 4s. The next column is 2 to the power of 3, so it can store 8s. So how do I store all the possible values? Well, simply if I want to store 0, it's just going to be 0. Okay, because I've got no 1s. But if I want to store a 1, then I'm going to put a 1 in that column, because 1 ones is a 1. What happens if I want to store 2? Well, I've got no 1s, but I've got 1, 2. Okay, because I've got a 1 in the 2's column. 1 times 2 is 2. What happens if I want to store 3? Well, I know I'm going to have 1, 2, but I've also got 1, 1. And that gives me a 3. If I want to store 9, I'm going to have 1, 8, no 4s, no 2s, and a 1. Because 8 plus 1 gives me 9. If I want to store 15, I've got an 8, a 4, a 2, and a 1. Because if you add them all together, you get 15. Now, we have names for the different size of number that we store in binary. Okay, the smallest bit is literally a bit. Bit stands for binary digit. Okay, they compressed it together, all right, to make the word bit. The bit can only be, basically, is a single binary digit, stores 0 or 1. A nibble is 4 bits, and then the whole thing together, 8 bits make a byte. Okay, or 2 nibbles make a byte, whichever we want to do it. Nibbles are basically smaller than a byte. Now, what you should be able to do, based on what we've just done, is convert the following binary numbers to denary. Alright, so if I were you, I'd hit pause, I'd have a go at doing the conversions, and then hit play again and check the answers. And assuming you came back, here are the answers for each of those different conversions. Did you get them all right? And I should be able to flip in the opposite direction and store each of these numbers as an 8-bit binary number. Okay, so hit pause, and if you come back, you should have figured it out. That 15 is that, this is 16, 37, 148, and our 256 cannot be stored in an 8-bit binary number. You need 9 bits to store it. Okay, and therefore we get what we call an overflow error because the number is now too large to be stored in the available number of bits. Now if you're doing GCSE computer science, is a bit where you stop. Okay, You can go on to the next video about doing binary addition. If you're doing A level, we've got continue. Alright, now if we want to store negative numbers, we've got two different ways of storing it. We can basically use sign and magnitude, or we can use 2's complement. Alright, so sign and magnitude representation basically, okay, is storing the sign in the number. I appear to have deleted a bunch of animations from the slide for some reason. Anyway, you have the most significant bit, which is the bit on the left hand side, is actually storing the sign, okay, and then the rest of the number represents the magnitude of the number, or the rest of the byte, sorry, represents the magnitude of the number. So if I want to store minus 127, I'm going to have 64 and 8, 64, 32, 16, 8, 4, 2, 1, all added together gives me 127, but the sign at the beginning of the number indicates that this is a negative number. Similarly, if I want to store 127, I will still have a 64 plus 32 plus 16, etc, 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 but this time the most significant bit is 0, indicating this is a positive number. Now, there are some problems with sign and magnitude, okay? Firstly, we've just reduced the size of the maximum number that we can store. We've effectively halved it, so we can only basically store from minus 127 to plus 127. Alright. Also, there's different data being stored in a word, so therefore the different bits mean different things, i.e. the most significant bit is representing the sign and the remainder of the number will represent the magnitude. This causes problems because programming logic then has to become more complicated in order to handle that. Alright. The second way of storing a negative number is to use 2's complement. Okay. So in the bottom table you can see this time actually the most significant bit is now a number, okay, but it's a negative number. It's minus 128. So that means that if I wanted to store, say, the value 85, all right, I have no minus 128s, but I have a 64, I have a 16, 4, and a 1, okay, because if you add 64 plus 16 plus 4 plus 1, you get 85. If I wanted to store minus 85, it'd be slightly different. I'd basically have a minus 128, and then what positive numbers am I adding on in order to get up to the value of minus 85. Now 2's complement, right, is effectively also halving the number size. You can see that if I want to store 127, that's the maximum possible positive number that I can store, alright, and the minimum possible number I can store is a minus 128. So we still have that negative of 2's complement, where we've got half the possible number from minus 128 all the way up to 127. However, we don't have to worry about different bits representing different data, because in essence the whole word is a number, and that makes programming logic a bit more simpler, okay, when you're designing CPUs, for example, to handle these types of numbers. So you should know now basically how positive and negative numbers stored in the base 2 number system, i.e. in binary. Thank you very much.